So what I wanted to cover today is talk about our next generation mobile applications and some of the network challenges we're seeing there. That's a nice segue into why we think mobile edge compute can be a real valuable system architecture for addressing some of those concerns. And the culminating, the cool part is I actually talk about supercomputing at the edge. So we have a demonstration of a system that we're working on. It's a collaboration, actually, and I'll talk more about it in a moment, about some of the progress we've made in developing just such a system. It's a real-world design example. And then we'll do a summary and wrap-up. So I think Jag had a nice intro to talk about how just the incredible growth we're expecting to see on data, right? And you know, down on this slide, you see just some of those, and I'll drill down into a bit more about what those applications might mean. But everything from cloud compute, transportation, M2M, some people like to say IoT, military 3CI, communications, control, command, intelligence, finance, health, etc. These are some of the promises and some of the needs, really, of the near future. The implication is, real-time communications, and this is something not so new to the wireless domain. Of course, we've been doing real-time communications for a long time. It also has implications, though, on data centers that are actually serving up this content, and there's a real parallel, really, to see what's going on both today in wireless, but also the future for data centers and the like. They need to think fast, and really the trend that we're seeing is a low latency trend here. So as we do drill down into some of those applications, again, it's just a real explosion of data, and I think this chart actually gives a real hint about what we'll see. So, for example, video and audio analytics or media analytics, both military and public, could be surveillance, search, intelligence, public safety. With that media, and especially high-definition media, you're going to be talking about the need to transcode that media, the need to analyze that media. Media caching, of course, if there's lots and lots of this media, especially high definition, what can you do to mitigate congestion up through the networks? Augmented reality, I'll have to say, I'm kind of a nerd, and I kind of like video games and stuff. It seems really cool. I don't know how much this is actually going to catch on, but certainly the need and the ability to support that would be there if we have this next generation capability in our network. So, imagine doing overlays, and if you go on the web, you can see lots of these examples where you can do overlays of marketing information wherever you look. If you walk into a mall and you can actually see what restaurants are available because it's around noon and I'm hungry, these kinds of things are possible. Targeted marketing, again, this is more about location-based services. Cloud computing, I keep looking forward to a time where I can have a very energy-efficient laptop, a cloud computer, if you will, which just has a thin client, and all the processing, all the storage, etc., is all happening up in the cloud and almost invisible to me. And then transportation, so that's part of this M2M. Transportation would be one subset of those. So autonomous vehicles might be a little further out, but certainly the ability to improve safety among vehicles would be a key application area. What all this means, really, as you roll it up, is streaming live data. And when we say live, a lot of this is happening in real time. So we're talking about a relative new paradigm where typically data centers, et cetera, to work on chunks of data. Here we're actually having to address the need on more of a real-time standpoint. Again, that lends itself to a need for really lowering the latency through these networks. As we look to the wireless standards themselves, certainly the bandwidth itself is increasing. You can see the standards there at the bottom, GSM, WCDMA, all the way up through 5G. So that bandwidth, the good news is that it's definitely going up, and that's helpful to me and you. But as we look out, especially as we look out to 2018 for the first field trials, maybe 2020 for production with 5G, there's a real challenge to be had there. So we're talking about an order of magnitude decrease in latency, going from 10 milliseconds down to 1 millisecond. That's LTE-A down to 5G respectively. And that's 150 times reduction from GSM. So that's just massive. And how to do that is really a challenge. Other challenges we see as we talk about this kind of, exponential growth in the data, this kind of need to support these real-time streaming types of live data, is potential bottlenecks further up in the network. So this is a source from Ericsson again here, but again, as we're looking at the congestion of the network, it'll kill your quality of service, could kill your latency, and so this is one area we need to improve on, for example. Location-based services would also be enabled better, and also if you could centralize that somewhere lower in the network, closer to the access, you can improve the congestion there. Again, the support for high-definition media that could only further congest the network, streaming media, and M2M, and we'll talk more about that in a moment, but M2M where you really push that 1 millisecond threshold. These are areas where we can't afford congestion up through the network. So what do? We take a look at it with mobile edge compute. Now there's consortiums out there that are definitely looking at the requirements, the standardization, and then the futures here for making these systems possible. So here would be your mobile edge compute platform, for example. Again, supporting all these various types of applications, right? And what you could do then is actually bring those apps. Some of them might have traditionally been in the data center, for example. Bring them out toward the edge so you can support that big data or the analytics thereof, the Internet of Things, social analytics, etc. In bringing those apps within the edge, you would expect to be able to, one, improve your latency, minimize the congestion, provide a better support for real time, a better quality of service to the user, better support those location awareness types of applications, and improve on your throughput. However, in saying that, mobile edge compute then creates its own system implications, really its own challenges. So ideally, again, as the folks preceding me mentioned, we'd have these essentially pools of processing and storage. And this implies a number of things. It implies scalability, certainly, low power, certainly. You have disaggregated resources, and you also have heterogeneous requirements to support GPUs for video, x86, for example, network processing and the like. And so you do have a heterogeneous setup. So you want to be able to openly support those heterogeneous setups with open standards, open hardware, and even open software. And then further, again, as Jag and the gentleman from Freescale mentioned, supporting NFV, SDN functions, centralizing your fabric management or the management of the system, and hopefully having that outside the network boundary itself. And then minimizing low power and TCO. If you're going to be putting a server or essentially a data center at all the access edge, it's going to be very key to drive down your TCO, minimize your cost itself, but also your operating cost. So IDT's been working in collaboration with a number of key folks and partners on mobile edge compute platform, just to address these kinds of things. As I mentioned before, media is going to be probably one of the single greatest and probably the leading application requirement for these types of systems. So what we have here is an example where we're tackling probably the foremost among those applications, which would be video analytics at the edge. Back in 2014, IDT collaborated with Orange and NVIDIA, and we announced really a prototype platform that leveraged NVIDIA's Tegra K1 mobile processors. These are very high performance processors, but they're very noteworthy in that they're not the most, the most intensive compute platform, but they're definitely the lowest power per performance. And we leverage those along with a low performance fabric, or a high performance, low latency fabric, so it'd be Rapidio in this case, to demonstrate GPU capability, a GPU compute capability that is actually scalable, and that would meet these kind of mobile edge compute needs. This is again a very much a prototype. So as you look to the picture there, that's actually the platform. There are 4 sets of essentially cards that look like evaluation cards. They very much were, but this again was a proof of concept. The requirement for mobile edge compute would look very similar for that video analytics portion anyway. So you'd have those 4 GPUs, and then x86 would be handling the movement of the data itself, GPUs providing the compute and analytics. And again, that low latency, high performance network here with PCI Express bridging into the Rapidio. It's a fault tolerant system, it's hot swappable, etc. And we can get really a best-in-class latency of 1.2 microseconds. And that's key, again, to support those real-time requirements. So lo and behold, just a little while later, Concurrent also got involved in this effort. And they've productized actually something that's based almost identically on that demo supercompute system. So this is the snapshot of the actual card. That card has 2 such Tegra K1 GPUs here, and then the Rapidio switching here. If you notice, there's a connector here that's a mezzanine connector. So this lower block diagram shows an additional 2 GPUs. So in total on this AMC card, and for the folks that aren't familiar with advanced mezzanine cards, it's a board about yay big, about yay high, about 60 watts. We're able to get 4 GPUs, a total of 384 gigaflops per GPU, 1.5 teraflops on a given AMC, and that's 12 teraflops possible in a 1U. I'll expand on that in just a moment. The key thing is we were able to scale that out, leveraging that low latency fabric. This particular slide covers the platform on supporting that heterogeneous requirement. So again, as I draw this out, here's the actual platform. This is this was an open standard platform. It's a 19-inch 1U. It's also compatible with OCP electrical and mechanical standards. So it has also been submitted into the Open Compute project for data centers and high performance computing. But this is a block diagram of what's really possible with this heterogeneous setup, right? So we've got anything from ARM, DSP FPGA, x86, GPU within that box. These are basically plug and play cards within this carrier platform, and then it's networked out through both of 20 gig Rapidio as well as Ethernet. If we take that server platform and you take 3 such GPU cards along with that x86 card, plug them into this 1U, you end up with about 18 teraflops in that single server. This could be standalone, so and it could also scale up to 4 boxes without even using an additional top-of-rack switch. However, if you want to further scale this to a rack scale setup, ProDrive is actually now offering publicly a 38 by 20 gig top-of-rack switch that's using Rapidio technology. So you could take that 1U server and scale it, say, up to 38 different 1U blades. In total, then, we'd be looking at half a petaflop in a given rack of GPU performance. I don't think you'll probably need that at the mobile edge, but that's just it gives you a sense of the density that can be achieved by this kind of setup. So to wrap up, as supercomputing at the edge, what we've got then is this system that's been built up. And we're doing work on it right now, actually. I wasn't, unfortunately, in a position just yet to show you some of the results, but we're actually running video analytics in the lab right now, and they're looking really good. I hope to share more of those, and certainly at the booth we can show you what this platform looks like and talk about what the applications are that are being run, as well as what the results are looking like. But you've got rack scale, with terabit switching. We've got a half a petaflop in demonstration today, and the next generation of the server card will actually go up to doubling the number of processor boards that can go into that. So up to a full petaflop per rack. Again, it's a 19-inch standard, OCP compatible, would be used mobile edge. It is heterogeneous, as we showed. And key to support that rack scale and to support these open initiatives is that the software is at least for the network itself, is open standard. It's open software, open APIs. The fabric management is coming available this month. That's also open standard, so they could be also leveraged into the management of that network. And then so is the RDMA and performance data path software functions. Those are coming available this month as well. So again, we will have a booth later today and have a demo of at least of some portions of the hardware there. So feel free to come visit us at the IDT booth. Appreciate it.